So, yes, please go to the github.com Stephen Beck / paddle and the crack detection. So under the convolutional neural network session, there's a link called crack. Over here. And then if you click that one, it'll pop up the notebook. And like I explained earlier, opening Colab is the easiest way of getting started with this. So please do that. Another thing I want you to do is to go to this Kaggle competition. So it's in the same notebook. Go to that, link, and you should be able to see the Kaggle competition. So Kaggle is an online platform where people upload data sets and let you have fun with all kind of data sets. There are also competitions. Some of those competition even have a monetary reward. So I created a competition over here on Kaggle. There's no monetary reward, sorry. But this competition over here is just for fun and to give you an opportunity to, take a look at what Kaggle is all about. For today's class, though, since this requires a sign up and, there's a little, finicky details, we're not actually going to do that. I mean, use this website, but the exact same set of data is available from the course website. So right below that, crack, notebook link, there's a link to data. And if you click that one, it'll download the exact same data set as the one in the Kaggle competition. And the data set essentially contains two folders, one called train, the other called test. The train folder is further divided into two different folders, crack versus normal. So crack is where you can find images of concrete with various types of cracks. And of course, these are pretty low resolution images, but you can kind of see the cracks in the concrete. And then obviously normal ones. So if you go to normal, you will see concrete samples, but this time without any cracks. And then obviously the goal of today's session, and I think largely the actual implementation is going to be a homework, is to implement your own convolutional neural network using PyTorch, such that you can classify crack versus normal. And the fun part is, well, this is totally voluntary. So if you don't want to do it, that's fine. But after you develop your own model, train it yourself with the data, you can make submissions of your prediction result. Results, or we'll see who even is going to bother to submit something. So we'll see about that. But in terms of that competition, so that's where the test folder becomes relevant. So remember, the data set is comprised of the train and test folders. Train folder is the one that you can use to train your model. The test folder is something that is comprised of a random mix of images. Okay. And they're not divided into normal versus crack. So technically, you don't know the answer. Although you could just take a look at the image manually and then use your human convolutional neural network to make that judgment. But what we're going to do at the end of the day is to run your model on that, images in the test folder. And for each of the images, we're going to export, not each of the images. We're going to export an Excel sheet that looks like this, or CSV file to be more precise. So we have file names, and then we have target labels. Okay. So right now there's a sample submission CSV file. It's all filled with 0. So, everything is normal is what, we're saying. But, at the end of the day, what I would like you to do is to, train your own model, let your model to, examine the images, and then, produce that CSV file. And once you have that CSV file, you can go to the competition site, make submission, and I put up all the details already in terms of how you could do that, and then I'll also walk you through today. And then based on your submission, your score will be automatically graded, and then whoever gets the best score will have an honor. There's no monetary reward, unfortunately. I have a few rupees if you want. Oh, I exchanged everything, but I'll look up. So that's kind of the plan for today. Again, during the class, I won't be able to show you everything. So largely, I'll leave it up to you to do it as a homework after this, this session. Hopefully tomorrow morning or, anytime throughout the week. There we go. So this is the crack detection notebook that I pulled up on Google Colab. So you should be seeing something similar to this. The first part of the notebook explains, how the Kaggle competition works, and then to, set up, to participate in Kaggle competition, you got to set up certain things. So you have to sign up for an account, and then you have to, get what's called an API key, blah, blah, blah. It's very easy, just some, inconvenience. So here's a kind of a walkthrough, which I'm not going to do. But instead, please go directly to this part, alternatively, ... So because we don't want to, spend time during the class for signing up for Kaggle and, things like that, here's a quick access, okay? So find that alternatively ... and then go below. And there's a code that contains a URL, file name, data directory, so on and so forth. That's the one that you want to execute. Oh, before I forget, today is probably an occasion where you want to use a GPU node. So go to Edit, Notebook Settings, and then select either T4 GPU or V2 TPU. So in that way, you can leverage the GPU power. and do the computation a little faster. So once you selected the GPU option, go ahead and run this cell. So this cell is purely Python and nothing really relevant to today's course. This particular cell that we're running right now is for downloading the concrete, crack images from a repository, and then after the download, it's gonna automatically unzip. So it's not really about machine learning. It's really just pure Python. And after you successfully run this cell, you will see this green checkbox. But also on your left, when you click this folder icon, you will see that there's a folder called data created. And inside of that, you have paddle, concrete crack detection. Yeah, and so on and so forth. So if you downloaded the file by running that cell, let's scroll down to the next cell where we have import PyTorch cell. And below we have a little bit of things going on. PyTorch, if you recall, has this called the CUDA engine. So CUDA is a GPU acceleration, stuff. And right now on Google Colab, we're using Google's GPU, right? And what that will entail is, torch.CUDA will become available automatically. If you turn on the GPU option, torch.CUDA will become available. Therefore, this if statement is going to be true, which then sets the default device into torch.device.CUDA. If you didn't turn on that GPU option, this will fall into the bottom line over here, where the device is going to be selected as, CPU is going to be selected as your device. Okay, so make sure that you see this line over here where device equals to CUDA. If it says device equals CPU, then you probably forgot to turn on the GPU option. Now, so unlike the other PyTorch sessions so far, today's session is I'm just going to be walking through the source code, because there's a lot to kind of write down. So it's going to be impossible to do it in a conventional way. But the first thing after importing PyTorch is to define a data set. Okay, so this is where you can this is basically the code showing how you could load the data. For loading data, for loading image data, one very useful library is called a Torch Vision. And Torch Vision is a PyTorch computer vision extension that comes together with PyTorch. So by installing PyTorch, you will have Torch Vision. So no extra installation. But in Torch Vision, there are two things to remember. Firstly, there's a thing called the transforms. Okay, so during the class today, we saw data augmentation, for example, right? We talked about, oh, here's a cat image. Even if you rotate the image, it's still a cat. Even if you scale it, it's still a cat, blah, blah, blah. All those kind of transformations are stored inside of this transforms library under Torch Vision transforms. So here, look at this line. We have transform equal to transforms dot compose. Okay. And by doing this, what you can do is to compose a different sequence of image transformation. Okay. So inside of the square bracket, what you can do is to give a list of transformations that you want to apply to your input image. Does that make sense? Now in this code, we have some, a few simple examples. One is called the transforms.grayscale. That obviously is a transformation which converts a color image into a grayscale image. Okay, so we're doing that because for the concrete crack detection, I figured the color, doesn't add much value. So, you can insert transform.grayscale. You could still maintain the color values, right? It's up to you. So I encourage you to actually experiment with this, especially if you want to get a better, better score for the competition. Transforms.resize is literally a image resize operation. So no matter what the size of your input image is, transforms.resize will convert that image into a specific size. And then during that, resizing, it'll squeeze the image or, whatever is necessary to, convert the original image into the new size. So here, I defined image width at 64 and the image height as 64 as well. So it's after the transformation, over here, after the transformation, the image is going to end up 64 pixels by 64 pixels. Obviously, that might be a little too small, too low resolution, right? 64 by 64 is like really tiny. So it might be harder to detect a crack, obviously. So maybe you want to play with that by increasing it to 128 or 256 or bigger. I forgot what the original image resolution was, but the original image resolution is not that great either. So there's got to be an upper limit. Which is 256 by 256 pixels. So that's the largest resolution that you can have. Again, feel free to play with it, see how the prediction accuracy changes. Now, these two are a little bit of technicalities, okay? So let me explain these two lines to you. So transforms.toTensor is a transformation, image transformation that transforms whatever data format that the previous thing might have into the PyTorch tensor. So internally, when the images are loaded, they are loaded as Py, which is a different data type than PyTorch tensor. So you must specify this to make sure that images are now stored in the form of PyTorch tensor. Okay. And then the bottom line over here, we have some weird thing called a transforms.lambda. And inside of the parentheses, we have torch.flatten. So the important keyword over here is flattening. So right now, in this example, we're going to be using the simple multi-layer perceptron. Okay. No convolutional neural network, no ResNet, nothing fancy. We were starting with a multi-layer perceptron expects a vector as an input, whereas a 64 by 64 grayscale image is a matrix that has 64 rows and 64 columns. So there's a size mismatch. So what this torch.flatten will do is to flatten, literally, by concatenating all the pixel values into a long vector. So 64 times 64 is 256. No, that sounds wrong. 2 to the 6, 2 to the 12, which is 4,096. Yeah, 4,096. So, it's gonna, flatten the pixels and construct a 4,096 dimensional vector, right? As a result of this line. So later, if you have an ambition to implement your own convolutional neural network, and convolutional neural network doesn't require a vector valued input. Convolutional neural networks can handle image itself. And in that case, you probably want to remove this line. But as far as the multi-layer perceptron is concerned, that line is necessary. So these two lines are kind of, necessary, post-process after you finish the image transformation. With that being said, there are obviously many other transforms available in PyTorch. So let me just show you a little bit. So here's a PyTorch documentation. The section for Torch Vision transforms. And then I think some part of the screen is cut off, so I don't seem to be able to see the full list of. Yeah, I don't seem to be able to see the full list, but that's fine. So here's one that we already know, transformed as grayscale, right? But there's a extensive list of things that you can do, such as padding. Here's a random affine transformation, so rotation and translation of the image and scaling. Here's a random apply, and then you can apply transformation matrix. Sorry, the transform. Here's a random crop. So the random crop will randomly pick a region in the image and crop it out. Here's random grayscale. So sometimes you convert some, image into a grayscale. Sometimes you just keep the color. Random horizontal flip. Again, sometimes you flip horizontally the image. Sometimes you don't. You can specify the probability of that happening. Here's a random perspective transformation. Random resize crop. You name it. All kind of geometric transformations and image transformations are available. Okay. And then you will see that there are two versions, random vertical flip versus vertical flip. The ones with random literally are the ones that happens randomly. If there's no keyword random, then it will be applied for all images, right? So for data augmentation, you probably want to introduce those random transformations on top of what you already have over here. But in this session, we're not going to explore everything. So I'll leave it up to you to explore different transformations. So there's a lot to play with, right, in terms of improving the accuracy. And then, so that's the first thing. The second thing is the data sets class. And the data sets module in Torch Vision, again, helps you read an image data set from a storage directory, and then parse that easily. So here you see this red highlighted line. Seems like there's an error. We have data set equals to data sets dot image folder, and then you put data directory. So here is the data directory. Okay, so data dir is defined as data slash something something above, and then under slash train. So I'm trying to read all the images from the training data set, right? And then as I read the training data set, please apply the transformation, is what this line says. And in that way, datasets.image folder functionality is going to read all the images in that folder and then associate those images with a label according to the subfolder structure. So remember that inside of that train folder, there was a crack folder and the normal folder. So PyTorch will automatically detect the folder name and then assign that folder name as the class label. So all the images in the crack folder, for example, will have the label crack. And then all images inside of that normal folder will be loaded with the label normal. Okay? Now, why is it giving me an error? No such file or directory? Oh, I downloaded it. Data DRR, data slash paddle concrete crack detection. Oh, for some reason, okay. So in that case, so I think the problem here is somehow we ended up, the paddle concrete crack detection folder inside of that, the folder with the same name. And I think that kind of messed up the whole thing. So the simple fix to this would be to add that to data dir. I don't know if you guys are seeing the same problem, but after changing the data dir to that, if you go back to this line and run the cell again, then voila, we have the green check mark here. Which means now we have loaded a data set, okay? Now, right below the data set loader, image folder, we have this weird lines here. So what's happening is first, After loading the data set, we're checking the length, how many images we have, and that's what determines the data set size. And what we decided to do is to set aside 20% of the training set for the validation set. So in the previous PyTorch session, we didn't, consider any validation or anything. We just train everything and then, sort of overfitted, our model. Now we're going to do it more professionally. So 80% of the training set is going to be, used for the training of the model. And then the 20%, the remaining is going to be set aside for the validation. So that's basically what's happening over here. And then random split is a function that will split the data set into two separate data sets. So random split is over here is defined under torch.utils.data. So this is one of the utility functions that PyTorch provides. And simply you can throw in your original data set alongside the list of sizes, and then PyTorch will, split the data set into two. Okay. And then finally, we have torch.utils.data loader. And then from the training data set, we create a train data loader. And from validation data set, we create validation data loader. Data loaders are sort of optimized pipelines. So data sets are literally, the actual data sitting somewhere in the storage device, right? And then data loader are literally the pipeline to, load the data, bring that to GPU so that the GPU can consume that data. And then PyTorch kind of, does it in an optimized way so that you don't waste too much of a computational resource. So I'm not going to go into the technical details on that, but some of the options that you can use in the data loaders is, first of all, the batch size. So here we have the batch size of batch size of 32. So we have 32 samples in one batch. No matter how big the training set is, each time we're going to read only 32 samples. And then this kind of goes back to the question earlier. Whenever we sample that batch, okay, each time we do the batching, we're going to shuffle the data so that the same set of images don't end up in the same batch, repeatedly. Okay, so that's for the training data. For the validation, we don't really need to shuffle anything, right? We just need to validate on a fixed number of samples. So in case of validation loader, we do not have the shuffling. So this is how you would load image data. Questions? Yes. Batch sizes are also, yes, hyperparameter. If you go with the too small of a batch, then your gradient will contain too much of noise, right? But if you go with the too higher batch size, then your computer may give up because there's not enough memory size to have all those images, right? But also the speed is going to be much slower with a larger batch. So you got to find the trade-off in terms of the batch size. Yes. We'll get there. We'll get there. Yeah. I think there was another question. You good? Okay. Sure. Standard image formats, PyTorch should be able to read them all. So JPEG, PNG, bitmap. Um, so should be fine. If you have some special image format, then you probably want to write your own code to read those special formats. Sure. Sure. Yes. Yes. Yeah. Yeah. It's the same thing. Yeah. Same thing. Same. Sure. Yeah. Not a problem. Other questions? Okay. So if this makes sense, now we're ready to move to the next cell, which is just fun displaying the loaded data set. So always the first thing is to make sure that the data that you loaded, right, looks good, right? And there's nothing peculiar. So I just plotted all the, I mean, not all, but some samples in the training data set. And then for each of the sections, we have the class labels. Seems like everything is okay, right? All right. So the hard part is gone. Now it's really, designing the model and have fun with training. So in terms of the designing of the model, this is how you would define a PyTorch, neural network model in general. So unlike what we've done yesterday, where we manually typed WB, all that kind of stuff, we're going to use what's called the NN module, neural network module. So, I hope this syntax is not terribly new to everybody. Class and then simple classifier is the name that I gave, to this guy. So you can feel free to have your own name, okay? But then this simple classifier will inherit this NN dot module. And this is kind of the basic syntax. Now, my classifier is comprised of two parts. And all the models that you're gonna write onwards will have these two parts. So these two parts are the most fundamental and crucial parts, okay, for defining a model. The underscore init, the initialization part. So this is in old C++ Java type of jargon. It's a constructor. So this is what's being called when the model is first defined. Now, what we do is we're gonna create a member called the linear one, okay, which is nn.linear. So nn.linear is essentially one single layer of perceptron, wx plus b followed by an activation function. So that one package is defined inside of nn.linear. So what we've done yesterday, right? We defined w manually, b manually, right? And then we define our sigmoid activation manually. That as a package is inside, sorry, except for sigmoid. W and B as a package is inside of that nn.linear. Okay, so it's a lot more convenient compared to what we've done yesterday. Inside of that nn.linear, what you need to define is the number of inputs and the number of outputs. Okay, so right now I have some generic values over there, but we'll get there later. Now, here's another linear layer. So my neural network obviously is comprised of two perceptrons, okay, stacked back to back. So linear 2 layer is another NN dot linear layer with different number of inputs. So the output of linear 1 is going to be the input to the linear 2, right? And then it's going to out some number of outputs is how the model is designed. In the middle, I have what's called an activation function. And over here, I'm using 10H, okay? Again, we today talked about ReLU, right? All kind of different stuff. Feel free to play with this, by changing it to ReLU, leaky ReLU, whatever it is that you might be interested in doing. But in this example, we have 10H. So that's the initialization of your model, okay? Now, forward is a function that is going to be called each time when your model receive an input. So whenever the model is given an input, that forward function will be called, okay? So that's where the actual computation happens. Init is the initialization, right? And then the forward is the actual computation. Now, for forward function, the input to forward function is some arbitrary value x, arbitrary input x. And then that x serves as an input to linear 1, whose output is lazily just called x again. I'm not very good at naming, so I didn't bother to change the name, but I could have, done something like this. Right? So maybe, to be more explicit, let me actually use this convention. So x comes in as an input to linear 1, which then spits out x1. The x1 then goes into my activation function, which is 10H. And that activation function will spit out x2, I'm going to call it. And that x2 goes into linear 2 layer. And then that linear 2 layer will spit out, let's say, x3. And that x3 is what is returned. Again, I put numbers there to make it crystal clear in terms of what goes in and what comes out. But in practice, you don't even need to, distinguish them. So far, so good? Yeah. So, this is kind of my favorite part of, PyTorch. All this WX plus B, 10H, sigmoid, all of this becomes like, like a Lego blocks. And then you can just assemble them together. So for example, let me show you how, you guys might want to, change this code. Let's say by, I don't know, adding one more hidden layer. Yeah, I want to do that. So let's say self dot linear 3 and then dot linear and then in this case I'll just take the number of hidden neurons and then just spit out the same or maybe twice more of hidden neurons or hidden outputs, right? And then let's say I defined another activation function called act function 2. This time ReLU, just to be different, right? And then I just assemble them together, right? So maybe x3 equals to self dot linear 3. Yes. Yeah, we'll massage that. Thank you. So yeah, This is why I don't like to put the numbers, as you can see, right? It's starting to be more confusing. So if I remove all this, so I just added the linear 3, and then let's say here I put self dot act function 2 x, and then that finally goes out, becomes the input to linear 2, and like what you just said, you could do something like this. Right? So it's kind of like playing with the Lego blocks, and you can, assemble them together. Um, Later on, you can. I mean, right now it's everything is kind of a serial. So the simplest way of assembling Lego blocks is just putting, stacking everything on top of each other. But you could also, build, something cooler by, assembling them in a weird shape, right? So you could do the same thing as well. So I'm almost making this up, but let's say for some reason, let's see if my small brain can track all this. Yes, you could do something like this for, no, sorry. This is not necessarily parallel. This is more parallel, I guess. Yes. Do you follow this? Well, forget about the number of, like the details in terms of the assembly. All right. So what I've done over here is I created a 2 branches of input. So the input X comes in. Well, actually, this is what I wanted to do, I guess. So input X comes in. That goes into linear 1, followed by activation function. So that is one branch. That same input goes into linear 3, and then activation. That's another branch, whose output is then sort of merged, right? So now we have kind of a parallel architecture. And this is actually a common technique that people use. And we're going to see some of this later in the class, actually. Okay. Yeah. So what I'm saying over here is designing an architecture with PyTorch is super simple. As long as you can, draw a flow chart, that flow chart could be implemented in the forward, function like this. So again, I strongly encourage you to play with different your own design of architecture and see which one performs better, and that's where kind of the fun begins. Um, in this class, however, I'm going to stick with the simplest example, and I just realized I went too far. So let's see if I can just undo everything. I came too far. Ah, okay, not bad. Yeah, yeah. All right. I think this is where it was. Yeah, this is where it was. So we just saw how to, define a model. Once you define a model, you can create a model like this. Okay, this line over here, model equals to simple classifier, and then for our problem, number of inputs is the total number of pixels, right? We flattened the pixels, remember, into 4,096 dimensional vector. So that's over here. And then number of hidden layers, hidden neurons, I kept it 4,096 for some reason. Again, you can change it to something smaller like 500. Doesn't really matter. I mean, it does matter. It will change the performance. So it'll be fun to observe how the performance changes as you change the number of hidden neurons. And then the number of outputs is 1 because we want a binary classifier. Crack equals to 1, no crack equals to 0, right, is what we want to do. So just 1 output is what we expect. So if I run this cell, at the end, it'll print the model. And then, the print will kind of give you a summary of what your model looks like. So you can kind of double check that, okay, my simple classifier is comprised of linear 1 layer, followed by the activation function, and then followed by a linear 2 layer. And the linear 1 layer takes 4,000 inputs, spit out 500 outputs. And then my activation is 10H, right? And then linear 2 layer will take 500 inputs, spit out 1 output. And that's really what this summary shows. Any questions so far? No, no, it's not redundant. If you think about it, you're transforming from n-dimensional vector to another n-dimensional vector. That transformation is not redundant. It can be transformed into all sorts of different things. So, no, that's not the case. And in fact, many of the architectures that we're going to see in the physics of aware deep learning will have layers that has the same number of inputs and same number of outputs. So we'll see some examples actually. Yes. Mm-hmm. Yeah, because linear 2 is defined to be num hidden, num outputs. And num outputs were defined as 1. Any other questions? Good. Well, if everything above makes sense, then the rest is really implementing the gradient descent that we saw. Here we have stochastic gradient descent algorithm. So yeah, look at this. Yesterday we had loss dot backward and then w.grad, b.grad, and we had to manually update the model weights and bias. PyTorch does that for you. So torch.optim.sgd is a stochastic gradient descent optimizer. There are other options, obviously. There's Atom, there's Momentum, there's Nestor, you name it. So if you go to PyTorch official documentation, you will see all kind of different optimizers, and feel free to choose and experiment with whatever you like to do. In this example, I decided to stay in a vanilla flavor. Okay, so here's SGD, but when you apply for the competition, feel free to, and I encourage you to actually play with different optimizers and such. But regardless of which optimizer you choose, these are the two most crucial input variables for the optimizer. The first thing is the things to be optimized. So an optimizer is a generic tool that will optimize whatever you want to optimize. Now you have to specifically say, hey, the thing that I want to optimize are model parameters. So model.parameters is a function that returns the entire list of model parameters that needs to be trained. And then I'm just, basically passing that to my optimizer. And then in that way, inside of that SGD optimizer, it'll take care of required grad true. You remember all this, things that you've manually done, right? Will be now taken care of by the optimizer. And that's pretty much it. Now, So I guess, oops. I'm gonna run this cell. And then the next cell is really the training loop. So I'm gonna go directly to this for loop over here. So I have set the number of epochs to be 100. So that means I'm gonna run 100 iterations, 100 rounds of training. For each epoch, now what happens is, first I set the model to training mode. Okay, so when model.train is specified, then PyTorch will understand that, oh, this person is trying to update the model. So it's going to track the computational graph and all that. So kind of equivalent to requires grad true that we saw yesterday, right? And then inside of that, the running loss thing is just for the visualization, so don't worry about it. So inside of that, for loop is another for loop where we go about the training loader, okay? So inside of this inner for loop, the training loader each time will spit out a batch, okay? And the batch size was 32, right? And then let's say you have 100 images. What's gonna happen is, it's gonna return first 32, and then next 32, so total 64, and then next to 32, which is total 96. And then the next batch, we're gonna have 4, okay? And then that is one round of iteration, what defines one epoch. So one epoch usually means one cycle of seeing the entire training samples, okay? And after each epoch, the train loader will shuffle the images, divide the batch again, and then we're basically repeating that whole process 100 times. Does that make sense? Yeah. So that's what's going on over here. The rest is, I mean, I have written down over here, what's, exactly going on. So first I move the data to the GPU device. So remember, when we first set the device, CUDA available, device was set to GPU or CUDA. So initially the images are loaded on your CPU memory. And by doing this, we're uploading everything to GPU. And now we're ready to do some high performance, computation. Step 2 is to call the model on the batch of inputs. And then as a result, the model will produce some predictions. Those predictions are then provided as input to what's called a loss function. Okay, I'll get to the details of the loss function in a minute. And in the loss function, we're comparing the model prediction against the batch label, the ground truth label, and produce the loss value. And then step 4, this is something you already know, except that after the back propagation, instead of you manually updating the parameter, you just simply call optimizer.step. And optimizer.step is that W minus learning rate times the gradient, right? That formula in case of SGD. In case of momentum, it's going to take care of the velocity, blah, 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 right? So no matter what optimizer you use, just call optimizer.step is all you need to do. And that's one cycle of model training. And then the rest is really just the evaluation and visualization of the training progress. I'm not going to go into every single details, but things should be pretty straightforward if you look at the code after the class. One last thing I want to mention before wrapping up is the loss function. And again, I'm lazy this time. So yesterday we defined our own loss, but PyTorch has a whole library of loss functions that you can choose from. So in this example, I'm using the loss function called the BCE, binary cross entropy, with logit loss. It's a quite mouthful name, but you could also do MSE loss or some other loss that you are aware of. Okay. I guess we haven't had a chance to, compare different loss functions and all that in great depth, because in physics-aware deep learning, only thing that we care is going to be mean square error. So MSE loss is probably the only thing that matters in this context. Computer vision, however, you may need the cross entropy, you may need hinge loss. Professor Khanna mentioned briefly about hinge loss, things like that. But since we're not primarily focused on computer vision problems, we're not going to bother to get into that. So that's really it. And if you run this cell, you will see that something is going on. And then notice that not only the training loss, but also the validation loss kind of goes down together. So that's a good news. The current setup, obviously, I stayed at the vanilla flavor. So simplest model possible, simplest optimization solver, simplest everything. I reduced the image size, probably too much. So it's not going to go too far. It's not going to be terribly accurate. But this is a good starting point, right? So again, let me repeat. Please go back and change the model architecture, do your own experiment, blah, blah, blah. See if you can beat the score. Yeah. And after you get the result, here's the model evaluation code. So the code in the bottom are basically some helper functions for you to evaluate the accuracy of the prediction of the model. You can see that on the training data set. After 100 epochs of training, the prediction accuracy is 64%, which is slightly better than the coin toss, but still, not very satisfying or impressive. Validation data set, we have about the same, accuracy. So again, this is probably the worst possible model. So hopefully what you develop is going to be much better than this. And I've seen, things around 80. So, maybe that is a good kind of an internal target to have at the beginning. And let's see who's, going to get the best score. And then in terms of competing for the best score, at the bottom, I've written a code to export all the, test result into a CSV file. At the end of the day, this guy will produce a submission.csv file in your hard drive or that, Google Drive. All you need to do is to download that and then, go to Kaggle, submit it, and then voila, you get your submission score. Okay? Yeah. But don't cheat. There's no point of cheating. By cheating, what I mean is, manually take a look at the images and then determine, what's in there, which is certainly doable because we don't have a whole lot of test images. So yeah, we have only 100 images, so it shouldn't be terribly difficult for you to go over manually and then write down the file name. But yeah, what's the point, right? There's not even a cash prize. It's for the learning purpose. So have fun with it, okay? And let me know if you have any questions. By the way, my email address is BAEK, my last name, at virginia.edu. So not only for this session, but also throughout the course, if you have any questions, feel free to email me and I'll be happy to answer your questions. Or you can also just come to class a few minutes early and then I'll be happy to answer questions in person. So, one last question and then we'll wrap up. Yes. Yeah, the weights are just, keep updated. Because if you think about the gradient is like the gradient operators are linear operators, which means the gradient of the sum is the same as the sum of the gradients, individual gradients, right? So even if you divide it into batches and take the gradient for each individual batch, the summation of those gradient is the same as, right? So it doesn't matter. At the end, we just add everything. All right. Thank you all. And we'll see you tomorrow. Please do the homework because tomorrow we're going to go into physics informed neural network. And then for that one, I'm going to assume that everybody knows and are familiar with the model training, at least at the conceptual level. Even if you cannot write it from scratch, from empty, clean sheet, I will assume that everybody understand the syntax. Okay, so please do the homework and have fun with it. And I'll see you tomorrow. Thank you.